That's exactly what I expected. I was planning to. Why have to take care of there? I know, but.
Okay. We're going to do a couple of different things. I'm going to look at these electrons. We're going to see that they are different from one another in terms of what their environment, what their immediate environment is. That's going to reveal itself to us in terms of the shape and the size of the orbital that they're in, which is also related to their energy. And from that, we're going to be able to have a shorthand that we can use on the periodic table that we're just going to call electron configuration. But before we get to that, we can do a little bit of theory. It's only a tiny bit of theory. That when we get to electron configuration, this 1s2, 2s2, 2p6, 3s2, 4p3 kind of notation that we're going to get. The theory is going to explain why the S is the S, and why the P is the P, and why the S is 2 electrons wide, and why the P is 6 electrons wide, and why the D is 10 electrons wide. Okay, let's do a little bit of this first. It's underpinned by some conceptual math out of quantum mechanics that are called quantum numbers. And 4 quantum numbers will describe completely the environment of the electron. Those numbers are N, L, M, and S. Now, in recent years, they've changed the names of the numbers from N, L, M, and S to N, L, M subscript L, and M subscript S. They must have had a good reason. S must have been interfering with something else, somewhere else. Okay. But don't worry about that. No 2 electrons are the same. And if you can describe an electron in terms of 4 quantum numbers, what that means is that no 2 electrons are allowed to have all 4 of these quantum numbers be the same. Okay. QN is my abbreviation right there for quantum numbers. Here are the quantum numbers. The first one is N. N is the principal quantum number, and we can't do anything with the other 3 until we know what N is. N, these numbers, these 4 numbers are top down. You have to know what N is before you can predict what L is. You have to know what L is before you can predict what M is, and you have to know what M is before you can predict, well, no, S is independent. S has independent values. But they are hierarchical. This is the principal quantum number. And it describes size. Not size of the electron, but size of the orbital. Okay. N has integer values. You all know what an integer is? An integer is a whole number. So this is just whole number values, 1, 2, 3, 4. And what they represent is the period number. So hydrogen and helium are in period 1. Periods are the horizontal rows on the periodic table. Hydrogen and helium are in period 1 on the periodic table. That means that both of those atoms contain electrons whose principal quantum number n equals 1, because they're in period 1. If you're a lithium or a beryllium or a boron or a carbon or a nitrogen or an oxygen or a fluorine or a neon, you'll have electrons that have n equals 2, because those atoms are in period 2. Okay, that was straightforward. L is called the azimuthal quantum number. Anybody know what an azimuth is? Anybody fly a helicopter? You learn to fly helicopters, you have to know what your azimuth is. An azimuth, let me tell you what the real definition is. It's about geometry. Oh, okay. Or there's an astronomical definition of it as well. An azimuth is the direction of a celestial object from the observer, expressed as the angular distance from the north or south point on the horizon to the point at which the vertical circle passes through the object's intersection on the horizon. Okay. Yeah. It's about spherical geometry, is what an azimuth is. And what azimuth tells us it describes shape. It's going to describe shape in terms, I'm not going to write that down. It describes shape in terms of spherical geometry. Okay. After we show you what a couple of these are, then you might be able to figure out what the number means. We'll see if we can figure out what the number means. Okay. The values of L are integer values between 0 and n minus 1. So if we want to know what the possible values of L are, we have to know what N is, because L depends on N. Okay? All right.
Is L equal to 0?
L is absolutely equal to 0 quite a lot of the time. Okay. Here are our possible answers. When N equals 1, when N equals 1, for the atoms that are in period 1 on the periodic table, what are the possible values of L? 0. L can be any number, whole number, between 0 and n minus 1. So there's going to be a 0. And then the next number up would be n minus 1, 1 minus 1, which is 0. So there is only the possibility in period 1 for L to equal 0. When n equals 1 and L equals 0, this gives you something called an s orbital. And an s orbital is spherical. We are going to get used to drawing blobs of electron density on our axes. There's 3 dimensions that humans are aware of. They're x, y, and z. At the intersection of these 3 axes, the x, the y, and the z, that's where the nucleus of the atom is. Outside of that atom, there is a cloud, an orbital, where you have a probability of finding the electron. If that electron belongs to an s orbital, then that s orbital is a sphere of orbital electron density centered at the nucleus. The probability of you finding the electron at the nucleus is 0. Electrons don't belong in the nucleus. There's something incredibly mysterious called the nuclear force keeping them out. Can't get through. But there's a spherical blob right there. And anywhere inside the blob, other than the nucleus, you have a probability of finding the electron. Outside of this sphere, probability of you finding the electron falls to 0. Okay? So these little shapes that we're going to draw, these are probability densities of you finding the electron. Okay? When n equals 2, the value of L can be any number between 0 and n minus 1. So this can be any whole number between 0 and 2 minus 1. What is 2 minus 1? 1. So we're going to have 2 variations. When L equals 0 and L equals 1. When L equals 0, this means that you have an s orbital. Put a gap between those. which is the shape of a sphere. Two tells us size. One tells us size. N represents size. L represents shape. When n equals 2 and L equals 0, I get another sphere, but it's bigger than the first one and it sits completely outside of it. Okay? And then L. L, when it's 1, gives us something called a p orbital. And a p orbital is shaped like a dumbbell. So if I had X, Y, and Z, the shape of a p orbital looks like that. It's a balloon, and you've pinched it down at one place, right here, because at the nucleus, there can be no probability of you finding the electron. Probability of you finding the electron at the nucleus is precisely 0. There are no electrons at the nucleus. So I have a blob of electron density on the left and a blob of electron density on the right. Okay. When n equals 3, these are the elements in the third period. L is allowed to have values between 0 and 3 minus 1. So the values for L get to be 0 or 1 or 2. If L equals 0, you're an s orbital. If L equals 1, you're a p orbital. Guess what you are when L equals 2? You're a d. These names are the names of the blocks of the periodic table. We have an S block and a P block and a D block. And D orbitals are cloverleaf shape. This is my X, my Y, and my Z. D orbital looks like that. It's three-dimensional. It has depth, but it has no electron density at the nucleus. Okay. So I said that this value L represents something to do with spherical geometry with only the information that's on the board, can we guess what the integer values 0, 1, and 2 for L actually represent? It is there, but you know, nobody's ever asked you a question like this before. This is a math question that says, look at this picture and pull the math out of the shape. L represents the number of times that the probability of finding the electron falls to 0. It's just a sphere. It's just a sphere. It has no breaks in it. None at all. Whereas this is cut in two. We call that a node. That's a node. And p orbitals have one node. L is the number of nodes. If I look at the d orbital is cut in half that way, and it's cut in half that way. L's the number of nodes. L tells us, like if you had a big squishy balloon, we do have balloons. I always keep a drawer full of balloons because we are going to need them. We blew up a balloon and then just squished that balloon down in the middle so that it had lobes on either side. We'd have put one node in it. I might be able to do that with my hands. There's zero chance of me being able to then also squish it the other way, sideways, and get 4 lobes. But you could see how that could be done, right? Yeah. Okay. That's the first two. Our quantum numbers are N, L, M, and S. Guess what the next one's going to be for L? I'm not going to do L, but in if N equals 4, right? How many periods are there on the periodic table? Currently there are 7. There's the potential for us to find more elements, or if we don't find them, synthesize them, make them out of nothing. That's what all the new elements have been man-made. They might exist somewhere else in the universe, but we've been creating our own elements for a while now. There are 7. So N can keep building. When N equals 4, you're going to have the opportunity to have L equals 3. Guess what L equals 3 is? That's an F orbital. One of the students asked me on Monday, are we going to do the F block? No, the F block is far too complicated and the elements are far too rare. You're never going to come into contact with plutonium. You should never come into contact with plutonium. Okay, so we're going to leave the F orbitals alone, the F block alone. All right, so the next one is M. It is now called M subscript L. And they've renamed the last one that we're going to see, S, as M subscript S. I don't like it. They must have had a good reason. I don't know what the reason is, but I don't like it. M is the magnetic quantum number. I think technically we can call this that there's a term that involves angular momentum that I think some people have been trying to squeeze into this name. Well, Wikipedia just says magnetic quantum number. There is some, I think there's a move afoot to change its name into something a little bit more specific. Okay. All right. The magnetic quantum number, and what it describes is the number of possible permutations. Okay. All right. Now ML has values in the range, integer values, from minus L all the way through 0 and out the other end to plus L. Let's think about that. If you are an s orbital, what's your value of L? 0. When you're an s orbital, the value of L is 0. So the value of M is allowed to be negative 0, 0, or positive 0. When L equals 0, M, now subscript L, equals 0. What this tells us is that there is one permutation that there is only one kind of s orbital per period. In period 1, there is an s orbital that is small. It's a small sphere. In period 2, there is an s orbital that is a sphere, but it's bigger than the s orbital that was in period 1. And in period 3, there is an s orbital, just the one of them, and it's bigger than the one for n equals 2 or n equals 1. Okay? That's what it means. If you are a p orbital, what's the value of L for a p orbital? Yeah. If you're a p orbital, L equals 1, which means that ML has possible values of -1, 0, and +1. That tells me there are 3 permutations. That tells me there are 3 different types of p orbital. There are 3 p orbitals possible. P orbitals are 3-dimensional. Here's the X, there's the Y, and there's the Z. The shape of a p orbital is a dumbbell or an infinity shape that passes through the nucleus but has 0 probability of you finding an electron at the nucleus. This one is on the x-axis. I'm going to call this px. Guess what the other 2 are? Yeah, I'm going to put one on the y-axis that I'm going to call py. And I'm going to put one on the z-axis that I'm going to call pz. And if you put them all together, they approximate a sphere. They're not really nice balloon shapes. They're actually skinnier, close to the nucleus, and then they flare out, they balloon out at the end, which means they fill in these gaps right here. But someone somewhere in the 1960s just said, draw them as balloons. It's easier to understand. It's easier to draw. They're actually more like kind of that shape. So they fill in these spaces in the extremities. They have to be skinny here, close to the nucleus, because I've already got an S and another S outside of it. You can't cram all the electrons all close to the nucleus and then leave the extremities untouched. Okay. All right. Let's look at the Ds. If you are a D orbital, L equals 2. What are the possible values for M? Those are some of the values.
Oh my God. Oh, it's so in between as well.
Yeah, it's every integer value. It's not just some of the integer values, it's every integer value between minus L and plus L, including 0 as an integer number. So my values are -2, -1, 0, +1, and +2. How many types of d orbital do we have? 5. There are 5 permutations. Okay. Hold on tight, because we're going to be drawing 3-dimensional clover leaves. Okay. So I need 5 X, Y, Z axes. not going to be doing math for a little while. We're going to be doing conceptual chemistry based around shape for a while. Give your brains a little bit of a rest, or use a different part of your brain altogether. Okay. Here's how we're going to do this. I'm going to draw a clover leaf that is entirely between the x-axis and the y-axis. So it's going to be 4 lobes of a clover leaf. None of which touches the nucleus. That one's flat, in the plane of the equator. The lobes are between the x and between the y. Okay? This is called dxy. It is between the x and between the y. Now, here's something kind of sort of interesting. The electron is allowed to be in this lobe. Probability of you finding an electron in that blob right there is real. And it's allowed to be in any of the other blobs as well. But it's not allowed to be at the nucleus. We have 2 nodes breaking these orbitals. So how does the electron get from being here to being there when it's not allowed to cross the nucleus? Remember a couple of days ago when I said electrons travel, and then I scrubbed the word out and I said travel is totally the wrong word. It's called quantum mechanical tunneling. It means was here, popped up there. Traveling is completely the wrong word because you associate traveling with moving along a path, and that's not what they do. They're infinitely more mysterious than that. Okay. They have a probability of being there. They pop up and they go away. And we can't follow them. We don't know. We don't know. There are lots and lots of smart people, and they're close to an answer, but it's beyond me. All right. If that's the xy, and the electron density is between the x and between the y, then perhaps I could do between the x and the z. We would call that the dxz. You will be asked to draw shapes of orbitals on a test. It is a thing. You are supposed to retain some of this information. If I can do it between the x and the y and the x and the z, then perhaps I can do it between the y and the z, right? This one's a bit trickier. These 3 are a subgroup to themselves. Those 3 do not put any of their electron density on the X, the Y, or the Z axes. So these three orbitals are called non-axial. And if you decide to stick with chemistry, by the time we get to inorganic chemistry, which is a 3000 level class, we reveal that the non-axial, and then the other two are going to be axial. The non-axial and the axial are responsible for the differences in shape and color in all the transition block. And it's a beautiful piece of chemistry. It really is. Okay. So these are the two. We've just let the cat out of the bag. These are going to be axial. These are going to have their electron density be on the axes. So let's do that. I've made these look more like p orbitals than d orbitals. I'm going to make these be a bit bigger. Okay, let's put something on the X and on the Y. So this is on the X axis and on the Y axis. When you compare that one, the fourth diagram, to this one, the first diagram, this first diagram, the red ink does not touch the black line. Here, the red ink cuts, the lobe cuts right through the middle of it. This is called x squared minus y squared. And then that leaves us one left. Okay, now here's a bit of a quandary because if I know that this one has to have electron density on the Z, because we haven't used that yet. But if I put it between the Z and the X, that means that the X kind of doubles up. And if I put it between the Z and the Y, then the Y doubles up. So this one's an anomaly. This one's different than the others. It looks like a giant p orbital. With a donut around its middle. The life preserver. And this is called the dz squared. In general chemistry and in organic chemistry, which is the chemistry that usually follows it, the researchers don't particularly care what the X, the Y, and the Z axes are. So I remember as an undergraduate doing the math for this and saying we could have easily made that be the dx squared and had the dy squared minus z squared. Okay, they're interchangeable. For inorganic chemists, they're a minority. There's not so many of them in the world compared to organic chemists. The z-axis actually is important. The z-axis gets to be the axis where metals bond to each other. So at much, much higher level classes, the z-axis is the axis that we keep separate from the bonding axis in inorganic chemistry. But in general chemistry, we don't care. These are all equal to each other. Okay. All right. That just leaves one quantum number left. Well, while we're here, we can predict something about the next quantum number. We have enough information already to predict what the next quantum number is going to tell us. There's only one type of s orbital per period. How many atoms wide was the s block? 2. So how many electrons go into that s orbital? 2. There are 3 types of p orbital. How many electrons wide is the p block? Boron, carbon, nitrogen, oxygen, fluorine, neon. That's 6 atoms. That's 6 new protons. That's 6 new electrons. The p block is 6 electrons wide, and there are 3 orbitals that can hold those electrons. Guess how many electrons each orbital holds? 6 divided by 3, 2. How many types of d orbital are there? How many electrons wide is the d block? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. It's 10 electrons wide. Each of these orbitals holds 2 electrons, maximum. It can hold 0, 1, or 2 electrons. So we just figured that out without even knowing what the next number is going to tell us. Each orbital can hold a maximum of 2 electrons. All right. This quantum number used to be called S. If you go back and you find a book that talks about quantum numbers prior to the name change, this is called S. It's now called M subscript S. This is the spin quantum number. Spin is a much misunderstood property. Can abbreviate its meaning. Spin only has 2 values. For electrons, electrons have spin of either -1/2 or +1/2. Spin is like the north or south pole on a magnet. Magnets can either be north or south, and you cannot put norths together in a box. If the box is the orbital and the electrons are magnets, you cannot put 2 of them pointing the same way in the box. They want to be spin opposed, okay? So we have an electron and it's moving. That generates a magnetic field, and that magnetic field can either be up or down. +1/2, -1/2, okay? So this number is independent of the other 3, but the other 3 tell us what the size, shape, and permutations are. Friday, we'll start stuffing electrons into these boxes, okay? All right. Oh, I started grading your tests. I graded some of them, not all of them. Sit tight, it'll happen.